Welcome to Deep Dive. I'm Margaret Leinen. I'm the director of Scripps Institution of Oceanography at UC San Diego. And in this series, I speak to scientists from Scripps Oceanography to take a deeper dive, a deep look into their science. And today I'm joined by Nathalie Zilberman. Dr. Zilberman is an assistant researcher here at Scripps, and she is a specialist in the warming, circulation, and dynamics of the ocean, especially the deep ocean. And here at Scripps, she also, in addition to her own research, oversees the data and production of what's called Core Argo and Deep Argo. And I'm going to have her explain what those are. But she also serves outside of Scripps as the co-chair of the Deep Argo Mission. So let's unwrap that for you. And welcome, Natalie. And I'm going to start by asking you a little bit about your own research, and then we'll talk about Core Argo and Deep Argo. So why don't you give me a little bit of introduction to the work that you do on warming, circulation, and dynamics?
Okay, sure. So what I'm working on is, as you said, ocean warming and ocean circulation, and interested in large-scale processes. By this, I mean across basin or interbasin circulation. Those studies are based on Argo data. So Argo floats measure temperature and salinity. Some floats can measure between the sea surface and 2,000 meters, and others all the way to the ocean bottom. And from the measurements of temperature and salinity, you get density, and from that you can get an estimate of where the currents go and how strong they are. And what I'm interested in is where the heat that is accumulated in the ocean goes, how it's transported. I've been looking at deep western boundary currents. Those are currents that are flowing typically below 2,000 meters depth all the way to the ocean bottom. I went at sea in May last year to deploy deep floats along the Tonga-Kermadec Ridge, just northeast of New Zealand, to study a deep western boundary current there. And we also took the opportunity to test oxygen sensors that are mounted. Some of them are mounted on Deep Argo floats, trying to improve the accuracy, stability, and precision of the sensors, because there's a strong interest for ocean deoxygenation that is in the deep ocean, mostly affected by ocean currents. So that's where, that's why we're doing this. And so there's a strong interest on prediction of the ocean deoxygenation, and there's pretty big question marks into it because the amount of data is very limited. That's the first part. The second, I should say, is a lot of my research is on technology development. I talked a little bit of it, about it earlier. So making floats as good as they can be, and the quality of the data as good as it can be is important, especially at Scripps. Scripps is the only institution of the US Argo Consortium where all the floats are built in-house. And the Scripps team takes a lot of pride of building the best floats in the business. So a lot of effort goes into making the floats last as long as possible and maintaining a strong collaboration with sensor manufacturer. And then a third part of my research, now I'm going to 4, is to looking at sea level. That's something that I've been more and more interested in, and that's because I'm interested in ocean heat content, and a significant part of sea level change is due to expansion of volume of the ocean. That is due to warming, the increasing of the warming of the ocean. And I've been looking at the impact of the changes in circulation of the deep western boundary current in the North Atlantic to changes in sea level. This is a brand new research, and that's something that Deep Argo can help us understand because it provides data every 10 days. And because of that, we can assess for the first time changes in sea level at regional scale and at internal scale. So it's something that is very new. The scientific community used to only understand changes in ocean heat content and sea level on decadal scales from repeat hydrography. But now with Deep Argo, we can resolve much finer spatial and temporal resolution. And then the last thing that I'm working on, it's in collaboration with David Sandwell at Scripps, is to use Deep Argo to measure ocean bathymetry. The floats can feel the ocean when they measure temperature and salinity all the way down to the ocean bottom. So they touch the bottom, and they have a pressure sensor, so they can assess, how deep the ocean is. And so we are working with David on comparing this brand new data set to echo sounding measurements, and actually the results are looking very good.
Natalie, for people who may not be familiar with Argo, can you explain how an Argo float works?
Yes, absolutely. They're called floats, but I think it might be confusing to people. It's actually a robotic platform. And so once deployed, for the core Argo floats, they dive to 1,000 meters depth, and then they will drift and get carried by the current. They don't have an engine. They will get carried for about 9 days, and then dive to their maximum depth of 2,000 meters and measure temperature and salinity on the way up. And so when they surface, they transmit data to satellites. They stay at the surface for just a few minutes, and then they start a new cycle. And those floats typically can live between 6.5 to 8 years, roughly. The deep ones, the model that has been developed at Scripps, they measure on the way down, all the way to the ocean bottom, 6,000 meters. That covers about 99% of the surface of the ocean. And then they rise up for about 500 meters or 1,000 meters. You can change that, actually. You can send a text to the floats and ask the float to change that. And then they will drift for 8.5 days and then rise up to the surface. They will also measure on the way up, and that's for providing near real-time data to ocean models. And then they will transmit data to satellite and start another 10-day cycle. And there's about 4,000 floats that are currently active. The US is committed to contributing to half of them. And out of those roughly 4,000 floats, there are 200 Deep Argo floats that are currently active, and about half of them are US floats. I should say also that within the US contribution, for the Deep Argo floats, all of the US Deep Argo floats are of the model that has been developed at Scripps, and the others are within that 50% are from the Scripps model that are manufactured by MRD.
So you mentioned the US contributed floats. How many countries contribute floats to Argo and Deep Argo?
There are about 38 countries that are contributing to Argo in general, and to Deep Argo 11 at the moment, and it's growing. Deep Argo require some added expertise, and I think it's a new program. It started 8 years ago, and that explains why there's less countries involved than core Argo that started about over 20 years ago now.
Natalie, I know there's a history of the Argo program here at Scripps. Can you tell us a little bit about how Argo started and Scripps' involvement with it?
Sure. So what I know about is that Argo really started, in the WOS era in the 1990s. And at the
Also
time,
is the world ocean
the
circulation.
world ocean circulation. And so at the time, those measurements were providing, the idea was to collect repeat hydrography section, cross basin of temperature and salinity. And so the motivation for Argo at the time was not temperature and salinity, it was velocity, because you had from floats the positioning of the floats at the surface, and you had an estimate of how long they would park at depth. And from that, you could infer the velocity at the subsurface. And that is important, is actually needed to be combined with temperature and salinity to estimate what is called the absolute velocity, the real velocity value. Otherwise, you have to assume a reference level of no motion where you think the velocity is zero, which is a bad assumption to make. So it's interesting, right? The beginning of Argo was motivated by velocity, not temperature and salinity. So the person who led Argo at Scripps at the time was Russ Davis. And so he's really the hero in the Argo program, right? He really developed the first Argo models ever. And so from that, there was a succession of different float models. If you go to Scripps, some of them are sitting at the lab, and you can see the different generations of floats. And then you can see that the floats are getting smaller and lighter, and there's no questions that the motivation is that having a float that is smaller and lighter leads to less energy consumption. And so the floats can actually essentially live longer. And so the lab that Russ was leading at the time, and is still called the Instrument Development Group, is now led by Dan Radnick. A part of it is dedicated to Argo floats, the other two ocean gliders. And so after Russ Davis, Dean Romick took over the Argo part and the Argo development. And now following Dean's retirement, Sarah Perkey and I are leading the Argo efforts. And so, as I said, the success of Argo is heavily dependent on the IDG group at Scripps and other institutions that are dedicated to contribute to the technology development of the floats and working with the sensor manufacturers to test, right, if the sensors are good, because unless you build floats in-house, you would actually purchase floats that are ready for deployments. But then it's critical that there are tests done in institutions like Scripps, so we can really keep manufacturers on their toes and making sure that the sensors are working the best they can.
Great. And I know that there are many people that refer to Argo data, probably not those that like you are helping to generate it, but many that are using it that have no idea that it began as an effort to find the level of no motion as opposed to the temperature and salinity.
Yeah, and in addition to temperature and salinity, so Argo is providing velocity at the subsurface. There are products that have been developed. One of those products is actually has been developed at Scripps and is sustained here, and provide velocity at 1,000 meters in the global ocean. So that's something that is useful for scientists who collect temperature salinity measurements, who are in need of an estimate of absolute velocity at a given pressure level.
So do you think Deep Argo will ever have oxygen sensors on it too?
The French groups have started already. They have doing it for a while. It's just the US haven't contributed to so far. And I think the reason is that the the Deep Argo oxygen data requires a heavy workload on the quality control, and also requires the availability of reference data. And that places burden on the need of personnel and time. And the cruise that I was on last year was motivated by the objective to improve the accuracy of the oxygen sensor, so that the requirement of, the time requirement for quality control would be reduced, and also the dependence on reference data. So making the data more reliable, so it's easier, it's just simpler to use, was the motivation. I would say that the manufacturers have been extremely helpful. At the beginning, Scripps just bought a few sensors, and then the manufacturers ended up providing free loaners, so because it's in their best interest, really. We provided them with a free opportunity for them to test their sensors. In total, we had all the oxygen manufacturers for Argo contributed to that effort, which was fantastic. And I will present the results of this voyage actually next week at the Argo steering team meeting.
Yeah. Now, Natalie, I understand that you led the technology development of Deep Argo. It's not just that you analyze data from it, but we have Deep Argo because of your work on that. And what was involved in the technology development?
A lot. It's well, I should say that I started being interested in technology development when I was on the ship that deployed the first deep solo floats, the first Scripps Deep Argo floats in 2014, and then deploying those floats in the middle of the ocean, and they're pretty small looking, and deploying them.
How big are they?
They're about 13-inch, wide, and it's just a little red dot in the ocean that you'll see. And I think I had the feeling of those, JPL folks who sent recovery, in space. It's just you deploy them, you wave them by, and then you're hoping they will work, basically. And so as part of this experience, I was very motivated to learn more about the technology, and in case of everything end up working well, but in case of things go wrong, it's better to be more knowledgeable. So we have a dream team here at Scripps, I should say. The Instrument Development Group, IDG, is just a jewel of Scripps, really. All the development on those floats, there's a reason why Scripps has the best floats in the business, because having an academic institution leading float development is key. The motivation is not profit. The motivation is to make the float as good as possible. And that's, I should say, the main reason why it's important that academia is involved in those ocean observing systems. And so I am involved in, I work with engineers. I'm not an engineer, but I'm sort of the intermediate between scientists who want to have the best deep ocean data, and I talk to the engineers about what's the objective. And it's and having the ability to just cross the parking lot and talk to them on a day-to-day basis, it's just a wonderful thing. I'll basically tell them what we're trying to achieve, and they tell me what is achievable. And so we find common ground and on what's possible, and given the resources of the program as well. So I'm involved in the development of the floats, the core solo floats, the 2,000 meters floats, and also the deep ones, but also the sensors. So as I talked about oxygen sensors earlier, I'm also involved into temperature and salinity sensors. The objective for Deep Argo was to have accuracy and stability similar to a repeat hydrography. So basically saying, oh, this float, this robotic platform can collect data of similar quality that you will have from a ship. That was a very ambitious objective. And I'm happy to say that thanks to a lot of work from international partners, this objective has been achieved. So it was a major milestone.
That is impressive. So you also are involved in data analysis from the floats. And what does that entail?
Well, there's, in terms of work, a lot of it has to do with quality control and comparing the Argo data set to shipboard data. Repeat hydrography is a key element of the observing system. Deep Argo is approaching the accuracy that can be achieved from ships, as I mentioned earlier. But Deep Argo is dependent on having this key reference data to assess how good the data is. So to make it simpler, I should say that any sensor that you use in space or in the ocean, it will drift after some time. And even looking at a same sensor model, not all sensors are equal, not all sensors are identical. So it's actually required to assess the quality of those measurements from independent data sets. So there's a constant work, and this is not me, this is the Argo data management team. That's an international effort, but Scripps is contributing to this effort to constantly check the quality of the data and making sure that there's no drift, that there's no offset, and the data is as excellent as it can be. And so we hear a lot about overlap that is needed between the ocean observing system, and that is one of them. So having repeat hydrography, having ocean moorings available where the data is very high quality in the deep ocean is very important for Deep Argo.
So does the Argo float have to go someplace, have to drift someplace close to one of these hydrographic sites in order to do that data analysis?
That's a very good question. I would say yes and no. So there's repeat hydrography pretty much everywhere. Just the sections are pretty far apart, but there are but there are regions where you need reference data more. If the water masses have a strong variability, say in the North Atlantic, then that's what the European groups are doing, is that they tend to collect hydrographic measurements where they deploy the floats. But Scripps doesn't, because most of the Scripps deployments are in the South Pacific, where the data, the dense water masses are very stable. And that's actually regions that we use for the calibration of the CDDs. It's that stable. So the float deployments from Scripps, and some of them are in the Indian Ocean as well, but I would say that most of the Southern Pacific ones don't require to have reference data nearby. So it depends on the regions where you're at. It's more or less important to have them. But having reference data is important, especially because I think there are still there's actually two CTD sensor models that have been developed and now provide temperature salinity at the accuracy that was targeted. So these are fine, but there are other sensors that are under development for which having reference data is quite crucial, yes.
So it seems to me that there is a tremendous increase in interest in data from the deep ocean. If I think back to maybe 15 years ago and what you would see at science meetings, obviously there were some talks about the deep ocean, but compared to today, there were many fewer. Why is it that people are so interested in the deep ocean now? Well, first, what do you define as the deep ocean? And why are people so interested in that now? And what have we learned from the Deep Argo deployments that we've had?
So as a physical oceanographer, not a biologist, I will define the deep ocean below 2,000 meters depth. Not 200, not 500, or not 100, 2,000. And I think the reason why physical oceanographers used to, tend to use that limit is because half of the ocean volume is below 2,000 meters. So they divide the ocean volume in two, the upper and the lower half. So upper ocean, deep ocean, 2,000 meters. So that's that. I think Deep Argo has played a key role in the interest of the deep ocean, just because, as I said, prior to Deep Argo, so prior to 2015, really, measurements of the deep ocean were only collected from ships or from ocean moorings. And those ocean moorings are deployed in remote and isolated regions. We tend to have 5 moorings on the moored array, and some of them are sustained, some of them are not. And in terms of repeat hydrography, those sections are far apart, 10 to 20 degrees apart, and they repeated on a decadal time scale. And that was the motivation for Deep Argo, actually, is to fill those gaps. And those are very large gaps. And so I think, especially working on ocean heat content and sea level, something that I witness is that there are a lot of work to close the Earth's energy imbalance. You must have heard of it, the excess heat that is in the atmosphere, and most of it is stored in the ocean. And then also to close the sea level budget. So I hear a lot about closing the global sea level budget, closing the Earth's energy imbalance. But how do you measure a global estimate, right? It's having a measurement every 10 years in sections that are 10 to 20 degrees apart, and having, 2 or 3 data sets that you average it over and you call it a trend. It's pretty ambitious, isn't it? So I've been interacting with the sea level community quite a bit, and there are a lot of talks right now into combining satellite data and Deep Argo data for closing the sea level budget. Because to close the global sea level budget, you need to resolve regional scales. You need to resolve interannual scales. Otherwise, your trend is biased. There are talks about, and that's true, about the closure of the sea level budget prior to 2015, and how the global sea level budget is not closing now. But the question is, was the global sea level, and the question is, why is it not closing now? But my question is, was it closing before for the right reason? Were we not averaging errors over the global ocean? Did we have it right? We certainly didn't have it right. We didn't have it at regional scale. We didn't have it at internal scale. And that's because Argo has been measuring at internal scales for the past 20 years in the upper half of the ocean volume, not the lower half. So there's big question marks. And the work that I'm doing on the North Atlantic, and that I'm very excited about, is actually half of my colleagues are physical oceanographers and working on Argo. The other is colleagues from the French Spatial Agency working on satellites. So it's really an effort to combine satellite data and in situ data. So having Deep Argo top to bottom estimates of ocean heat content and using satellite data, can we close the sea level budget? And I think that's the right strategy moving forward.
That's fascinating that the Deep Argo can be combined with the satellites that way. You mentioned before that we know that the ocean is taking up most of the heat. Are there enough Deep Argo data now to let us understand whether the deep ocean is warming?
I should say yes and no. It depends on where you're looking at. So on a global scale, no, there's only 200 floats that are currently active to reach. So right, to better understand why and how many floats are needed, maybe we'll have to take a step back and realize that the error in the estimate of warming trends are of similar magnitude as the signal right now. So you're looking at, say, you may have 2 or 3 millidegrees per year increase is roughly what you have in the deep ocean. And then you have a plus or minus 2 to 3 millidegrees per year. So how can you really tell that what you're measuring is correct? And that's based on historical data. Now, with Deep Argo, in regions that have been sampled to the target sampling, that is the objective, to have one profile every 10 days per 5 degrees. That's the target of what corresponds to the target of 1,200 floats. In those regions where Deep Argo floats had been measured, the Deep Argo float measurements have allowed to reduce the error by a factor of 10. So now, finally, we can see trends for which the error is 10 times smaller than the signal, which is, the situations where you want to be in. Otherwise, can you really trust those estimates? And so, so that's how the Deep Argo community could really tell, okay, objective has been reached, the temperature and salinity accuracy is enough to resolving trend well and with sufficient accuracy. So, but the problem is that, as I said, there's only 200 floats that are currently active. And for that reason, there's only little niche, little regions where there are, enough measurements that we can improve ocean heat content estimates or contribution to sea level. These are the biggest ones right now are located in the South Pacific. Scripps is one of the key contributors to that array. Another one that, PMEL has been heavily contributing to is the one in the Southeast Atlantic. And the European groups are contributing mostly to the North Atlantic one. So those regional pilot arrays have been intentionally implemented in regions that are deep, at least 4,000 meters or more, and on the pathway of those dense water masses that are carrying the deep ocean warming signal. So in some regions, yes, there's enough floats, but on a global scale, no, we need an additional 1,000.
So is the plan to expand by focusing on specific areas that are critical, like the Southwest Pacific and the Northeast Atlantic and Southeast Atlantic?
The plan is to expand those regional arrays. So those regional arrays had been deployed that way to showcase to the community, okay, if you had the density that Deep Argo is envisioning, what could we achieve? That was one objective of those regional pilot array. The second one was to demonstrate the ability of Deep Argo to measure temperature and salinity at the accuracy that is needed. And so this has been achieved. And now the limiting factor of Deep Argo is funding resources. There's not enough funding resources for deploying more deep floats than there are now. That's the sad reality. And yeah, additional funding is needed to deploy the global Deep Argo array.
Fantastic. I know from meetings all over the world that there is a very strong voice in the community, and not just in the Argo community, but in the climate community, in the sea level community, to get more Argo floats, and more specifically more Deep Argo floats. So that's fantastic. As you think about this, what are some of the other big research questions that can be answered by having this denser array of Argo floats and Deep Argo floats?
So aside from ocean heat content and sea level change, which are quite important, the third that I talked about is ocean deoxygenation. So below 1,000 meters depth, most of the changes in ocean oxygen are due to ocean circulation. So it's not something that you can, it's not solubility that is affected by water temperature is not a key factor anymore. So it's those two objectives are sort of intertwined in the sense that you need to know better the ocean circulation to understand better ocean deoxygenation in the deep ocean, because oxygen is basically carried by the current. But then oxygen can be used to understand ocean circulation better, but because it's a tracer initially, well, basically the ocean water masses as they are formed are rich in oxygen, and the amount of oxygen that they carry decrease as those water masses get older, as they mix with surrounded waters and such. And so learning about oxygen is actually, and how much oxygen there is in the ocean and how it is transported and how the concentration vary, helps to understand how the level of oxygen is decreasing in the ocean, but also helps to understand the ocean circulation better. And combined with oxygen and temperature and salinity, you can also, from neural networks, essentially those are functions that help you assess carbon parameters based on the relationship with temperature, salinity, and oxygen. So there's a lot of work right now into, okay, if you have temperature, salinity, and oxygen, how much do you know about carbon? That's techniques that have been tested in Europe Ocean with BGC Argo. And there are groups that are trying to, and those functions actually have been developed from the sea surface to 6,000 meters depth. So now there's interest in using Deep Argo for inferring ocean carbon and making comparisons with measurements from repeat hydrography. And that was one of the motivation, my personal motivation for trying to contribute to the improvement of those oxygen measurements from Deep Argo. So that's I think that's the next objective for Deep Argo is that I would see first is to have oxygen in the future, hopefully.
Are there other oceanographic problems that intrigue you that you hope to look at in the future?
Well, the ocean bathymetry is the new one that I touched on earlier, and really I've always used ocean maps since I've been a physical oceanographer, and having the ability to give back to that community that perhaps we take for granted because we all have the Smith and Sandwell bathymetry data, don't we, that we can make beautiful maps with. And for Deep Argo to have the ability to provide bottom depth, which, you know, that actually is providing data that is of comparable value to echo sounding. That was quite measured. David and I and other colleagues looked at comparisons. We used echo sounding for evaluation of how good the data is, and the results are really good. The errors that were found were of the order of 100 meters. That's all. So the main error in the estimates from Argo floats is due to the fact that when the floats measure the ocean bottom, you don't know where the float is, right? So we only know where the float is when it surfaces. And so there is this horizontal displacement, of course, because the float doesn't have an engine between the location where it measured the ocean bottom and the location where it surfaces. But there's actually, based on ocean model predictions, there's actually very widespread region where the displacements, given the vertical velocity of the float, it's actually pretty minimal. The displacement, we're looking at displacement of 1 to 2 kilometers, which is quite small compared to the uncertainty that you have from satellite. So, and there's work right now to have a look at the ocean model and then see how we can use ocean predictions to correct for that drift. So basically using ocean models to estimate drift between the bottom and the sea surface and ingest that back into the data set and make the correction of the ocean bathymetry from Deep Argo float that way.
Yeah, I think that most people, other than experts like you and Dave Sandwell, most people that look at those beautiful maps that show the seafloor or the bathymetry assume that it's been measured directly and don't understand that it's an inference from satellite data.
Yeah, I mean, 20% of it is measured, roughly 20% of it is measured from echo sounding, but the rest is inferred from satellite data. And the beauty of Deep Argo is that the Deep Argo can sample the ocean faster than the rate at which the ocean bottom is changing, right? So there can be a very strong and fast accumulation of data really quickly. And so I think in the past 5 years, just looking at the data set, over 10,000 measurements of ocean bathymetry data have been made. So, and that's with only 200 floats in 5 years. So you do the math. So having floats deployed everywhere could make a significant improvement to ocean maps. And coming to sampling and the ability of Deep Argo to collect data sets in those regions that I talked about where Deep Argo floats have been deployed, Deep Argo has collected over the course of 7 years as much deep ocean data as ships have collected in the past 70 years.
Wow. I should have asked you right away. It just occurred to me that if you say that you're measuring the depth, or essentially the depth of water with Argo, it implies that it goes down and hits the bottom.
Mm-hmm.
So how?
I mean, it touches it.
Yeah, so explain. I said that on purpose, hits, like, but I know that it's not that. But why don't you explain to people what actually happens?
Well, the floats are designed to become neutrally buoyant. So just wait a couple grams by the time they reach target maximum profiling depth, I should say. So there's a few Deep Argo float models currently active, and most of them, actually all of them except for the Scripps model, have the CTD, the temperature salinity sensor mounted vertical up, right? So it sits at the top of the float so that when the floats touch the bottom, it doesn't impact the quality of the measurement. Now, Scripps has, when the engineers decided to develop the new floats, they chose to use a glass sphere that is more efficient in terms of dealing with high pressure. And so it made sense to implement the CTD horizontally because the CTD, there may be other reasons, but one of them was to use the CTD as an anchor because you have a sphere and the sphere is sort of, it moves around and up and down in the water. But if you have a CTD that sits at the bottom like an anchor, you will have your float that would still straight, right? And that's important because you have an antenna that sits at the top and where you want to make sure that the antenna gets out of the surface when the float surfaces, right? And so because the CTD is mounted at the bottom of the float, it was important that the float wouldn't encounter topography violently. And so a bottom landing device, which is basically a wire, a 3 meters wire, was attached to the float so that when the wire touches the bottom, the float is so light by the time it reached that pressure that actually the contact of the wire to the bottom is enough for the float to not sink anymore. And the float knows that because it has a pressure sensor. So it was a pretty genius invention that the float lab developed for the deep floats.
I hadn't thought about that, that essentially the float is, almost neutral when it hits. Yeah, interesting. Well, anything else before we wrap up that you want to, something that I haven't asked you about that I should have?
No, I don't think so. I think we covered quite a bit. Thank you for the experience. It was great to talk to you.
It was great to talk to you. And Natalie, I'm just so thankful that you are here at Scripps and that you're working on this project. I think that I kind of alluded to it in my question about why we were hearing so much about the deep ocean, but it's because for the first time that we can actually do these measurements. And so much of oceanography and our understanding of the ocean proceeds at the pace of our ability to observe it. So by leading this effort with Deep Argo, you have just opened the opportunity for so many people to study the deep ocean and to really have us understand it more completely. And that sense of the ocean being, the deep ocean being kind of not changing very rapidly or not having a lot of variability, I think will go away.
Oh,
And
it's going away already. It's going away. And I agree with you, that when I started doing physical oceanography in classes, it was, the upper ocean is changing very rapidly and the deep ocean is very quiet. That's what we would hear, right? And now with Deep Argo, scientists are actually finding out that even wind can impact the vertical motion of isopycnals all the way to the deep ocean. The temperature salinity that can vary quite significantly in the North Atlantic, in the deep western boundary current that I was talking about, actually larger changes, significantly higher changes are in sea level are due to the deep ocean. So these estimates prior that were suggesting that the deep ocean is changing very slowly is, I think the root cause of it is that, except for moorings, that could actually measure temporal variability. The repeat hydrography was providing data that were collected, every 10 years. So it just didn't provide the means to resolve this variability. And that's why the common understanding was that the deep ocean was very quiet. But the truth is that there are a few regions where it's not quiet at all.
wonderful, fascinating. Thank you so much for the work you do with Argo, and thank you so much for taking time to talk with us about it today.
Thank you very much.